Those have even larger. The density there is about 1 gram per liter. The density of most like water is 1 gram per milliliter. If you take that milliliter and expand it to a liter, it's about the density there. Helium is less dense because air consists mostly of nitrogen and oxygen. The nitrogen and oxygen molecules weigh more. And helium atoms weigh a lot less. Interestingly, it's the same number. So if you have a liter of air and a liter of helium at the same temperature, pressure, they have the same number of particles. So this is hot air. Hot air is going to be less dense. Helium cell, helium balloon, and then hot air. So a combination of things here. All right, so these properties were introduced in section 4.1, so just review these. Gases can be compressed, gases expand to fill their containers uniformly. All gases have low density compared with those in liquid and solid. But here, when we talk about low density, you should think it's 1,000 times less than liquid, solids, and liquids. 1,000 plus times less than. Gases may be mixed in a fixed volume. Gas mixtures is something new that we're going to look at in this chapter. In the previous chapter, we looked at just pure gases, or it could have been air too, but here in this case, we're going to focus a bit more attention to mixtures. Gases exert constant uniform pressure in all directions on the walls of its container. Okay, this is a gas mixture here. This is air. Air consists primarily of nitrogen, like more than 80% nitrogen, or less than 80, about 79% nitrogen. Oxygen is about 21%, and then you have a trace amount of other gases like argon, helium, etc., CO2, water, small amounts of all. This would be dry air because there would be some humidity, humid and wet air. So taking this air and compressing it into a smaller volume, they decrease the volume, the pressure goes up. That we learned back then. But there's something in kinetic molecular theory of gases. We'll talk briefly about that. But gases consist of molecules in empty space. Mostly empty space. And so when we visualize a gas, we just have a container. If I have 1 liter of air, I almost have 1 liter of empty space and then a small amount of molecules. So 1 liter. In an ideal gas, the volume that the molecules or the particles take up is negligible compared to the empty space that's in. So it's like something like this. It's the space. And so the volume outside of the molecules in the gas is negligible when compared to the volume of the space of the molecules inside of that. So this is what we call an ideal gas. An ideal gas is like this. Whereas if the molecules took up a significant amount of the space in volume, then it's not so ideal. This is what we call a real gas. So this is ideal. The reason why we make differentiation between ideal gases and not so ideal is because of the way they behave. When you start cutting down the amount of empty space there, what happens is the gas particles can start to interact with one another. And there's more likelihood that this could liquefy. So if you compress a gas, smaller and smaller and smaller, the particles get close enough that they attract one another and then form a liquid like water. Like that. In an ideal gas, the attractive forces among molecules of the gas are negligible. Well, one way to keep the attractive forces negligible is to keep the particles very far apart. If the extremely far apart from one another, then there's no or very little chance that they're going to interact with one another. However, if you bring the particles close together, then what we have are attractions. The attractions are just, and we have different kinds of attractions in gases. For example, gases might be polar, so they could be positive and negative attractions. But even if a gas is non-polar, like helium, there are things that we call instantaneous dipoles that occur. That is instantaneous polarization of the electron cloud in helium. So even helium is not so ideal at very, very low temperatures. At very low temperatures, helium can collapse into a liquid. Okay. And so if we have mostly empty space here and large distances between the particles, we're okay. Another way to keep the particles from interacting with one another is to keep the temperature up. Because if the temperature is high, the molecules move faster. You know, if the temperature is low, then the molecules move slower. And so by placing the molecules closer together and then cooling it down, what's going to happen is it's going to liquefy the gas. Because not only are you getting the molecules close together, but you're slowing them down. If you slow them down, they have more chance of interacting with one another. However, you know, not so ideal is this. At low volume, at low temperature, it's not so ideal. Low volume because they're close together, and low temperature because they don't move so fast. The arrow tries to indicate how fast they're moving. And so here they're just moving slowly, here they're moving quickly. You know, they're going to be attractive forces. Some gases have stronger attractive forces than others. So for example, helium liquefies at 4 Kelvin, but if this were water vapor is going to liquefy at 100 degrees C. And so water has very strong attractions, and therefore to keep water behaving ideally, we need extremely, or not extremely, because you can break apart the water, because we need high temperatures and large volumes at low pressures. Then water would behave more ideally. So, you know, water doesn't like to behave ideally. You know, this ideal is just kind of an idealized state for a gas. You know, there's no gas that's truly ideal. The average kinetic energy of a gas particle is proportional to temperature expressed in Kelvin. The temperature and average kinetic energy are the same. It's average kinetic energy because not all the gas particles are moving exactly at the same speed. You know, some are moving slower, some are moving faster, even though this gas only has one temperature. The gas, let's say, is at 25 degrees C. Even at 25 degrees C, you know, all the particles don't move at the same speed, but the average will give a temperature of 25 degrees C, the average kinetic energy. And that is the average motion. Okay. The molecules interact with one another in the container without loss of total kinetic energy. So what happens is, you would think because of the collisions, things would start to slow down and get colder and colder because of colliding and losing energy. But it's not the case. These are what we call elastic-like collisions. Elastic, they just bounce off like rubber balls. Versus if you had soft clay balls, the soft clay balls would lose energy. You know, they'd stick to the balls or they'd stick to one another. But these just bounce off one another. They're moving quite fast. And they're like pool balls or billiard balls. Okay. So there are 4 things that we're going to characterize for a gas, and that's, you know, the pressure, the volume, the temperature, and the amount. The amount of gas is given the symbol N, and the units for N are moles. And so these are the things you want to know. You know, how much, what's the pressure, what's the volume, what's the temperature. It turns out we only need to know 3 of the 4. And we have this is the earlier law that we have P1, V1 over M1, which is here T1, you go P2, V2 over M2, T2. So N is missing here. And you have like an M1A, you know, some gas leak out of the container, if we added more gas, and then we could change potentially. So then we did calculations based on that. All right, we didn't cover all the laws. There's Avogadro's law. We'll talk about 14-3. Avogadro's law just says that the volume is directly proportional to the amount. So the amount is directly proportional to the volume at a given pressure and temperature. So this is another law. We had Charles, Boyle's, etc. And so another law is that the volume is directly proportional to the amount of gas. At fixed temperature and pressure. So there are different ways how we can think about this. So for example, if we have the reaction, 2 hydrogens plus an oxygen goes to, I'm going to make H2O gas in this case, 2 H2O gas. So this is going to be at an elevated temperature. Normally H2O would be a liquid. We'll make it a gas. In terms of volume, Avogadro's law just says this. If this is the amount of hydrogen I have, integral volume of the hydrogen, then I'm going to need half as much oxygen. And so I just take the volume of oxygen, which is going to be 1/2 the volume of hydrogen. And I'm going to produce the volume of H2O gas. The volume of H2O gas, this is a gas, not a liquid in this case, is going to equal the volume of the hydrogen, which is equal to 2 times the volume of oxygen, double the volume of oxygen. And so this is what we have. So if I have 1 liter, let's say, if I had 1 liter of hydrogen, how many liters of oxygen do I need? I need 1/2 liter. And how many liters of water do I produce? I produce 1 liter. And so this gives us easy stoichiometry. This is volume stoichiometry. As long as everything is a gas and at the same temperature and pressure, we could do volume stoichiometry like this. I don't know exactly what's going on here, but this is correct. What's going on here. And the volume of the gas, it just depends on the particles. So over here we have 4 particles of oxygen. Over here we have 8 particles of hydrogen. Well, 8 particles of hydrogen is going to take twice the volume. And this is going to make 8 particles of water. 8 particles of water takes the same volume as 8 particles of oxygen. Interestingly enough, gas is mostly empty space. The actual particle volume is negligible. Minuscule. And so that's what it takes. Here's Avogadro. So this brings us to gas mixture. There are what's going on with this graphic here? There are two different ways we visualize gas mixture. It's actually 3 ways. Let me erase this. The gas mixtures, the 3 ways that we visualize them are going to be based on some laws. There. Today I have a sample of air. When I say air is 21% oxygen, am I talking about 21% oxygen by mass or 21% oxygen by particles? That is, if I'm talking about particles, then if I had 100 particles of air, then 21 of those should be oxygen, and then 79 of those should be nitrogen. And then we're going to ignore the other stuff, because the other stuff is minor. Or am I talking about by mass? Because what weighs more, oxygen or nitrogen? Oxygen weighs more. So if I'm talking about by mass, then if I had 100 grams of air, then I have 21 grams of oxygen and 79 grams of nitrogen. And so when somebody says that air consists of 21% oxygen, what are they talking about? Because the two percentages aren't going to be the same. They're talking about particles? That makes the most sense. When you say logically, yeah, and in fact, that's what they're talking about. Air is 21% oxygen by particles or by moles. Moles is just number of particles or mole percent. And so what that means is if I had 100 particles of air, then 21 would be oxygen. Now, the percent by mass is a little higher because oxygen weighs a little bit more. So it's like 23%. Air is about 23% oxygen by mass, since oxygen's heavier. And so what we have is we have a mole fraction or mole percent. And so what we'll do is we'll do oxygen. You know what color they usually give oxygen? Blue?
Oh, oxygen is red.
Red. Yeah. Oxygen normally have red. So
Nitrogen is blue.
nitrogen is blue. So are these diatomic or atomic? You think? What do you think? They're diatomic, but I'm just gonna. They're so small. I'm just gonna draw them as dots. Here. I don't want to draw diatomic, but we're gonna have a lot more nitrogens. And so the mole fraction is, what is it? 21 out of 100 will be oxygen. And 79 out of 100 will be nitrogen, or 21% oxygen by mole, and 79% nitrogen by mole. We call it a mole percentage. Usually what people do is they'll just write percent, like this, percent, and OL. Usually the way it's written. But mole is just another way we can do dozen, 21 dozen, 79 dozen, or we can do individual molecules, 21 molecules versus 79 molecules. Now, this air, what we're going to do is we're going to have 1 liter of air at, what pressure should we use? 1 bar or 1 atmosphere? All right, we'll use 1 atmosphere here. Now, there are 2 ways of visualizing this. The first way is by Avogadro's law, or Avogadro's. If I have 1 liter, then how much oxygen is contained in that? So what I do is I separate out the red from the blue, and then just put the red on one side and the blue on the other. So if I did that, I'm going to have this. I'll put all the oxygen over here and all the nitrogen over here. And they're going to have the same number of particles per volume. Oxygen is going to take up a lot less space because there's a lot less oxygen. Nitrogen will need a bigger box for the nitrogen. And so we separated it into two boxes. One box of pure nitrogen, the other box of pure oxygen. How much of the 1 liter will the oxygen take up? 21% of the volume. In other words, it's going to take up 0.21. I'm going to get 0.21 liters of oxygen here. Or we say 21% by volume. And so if you look at the mole percent and the volume percent are the same. Yeah. And then how much? It's going to take 0.79 liters of nitrogen over here. So it's going to be 79% by volume of nitrogen. This is what we call constant pressure. Constant pressure. You know, of course we can compress the gas, get higher pressure in a smaller volume, or we can expand the gas, get lower pressure, greater volume for the same amount. So we've got to maintain the same pressure. And so what I'm going to get is I'm going to get 0.21 liters of oxygen at 1 atmosphere pressure. And so I'm going to get the same number of collisions with the wall that I had before. And over here, I'm going to have 0.79 liters of nitrogen at 1 atmosphere. There. It's Avogadro's. The other way of visualizing this mixture is by what we call Dalton's law. Okay, this is Avogadro's law. This would be Dalton's law here. In Dalton's law, the conditions are a little bit different. What I'm going to do is I'm going to separate these into two 1 liter boxes. So over here, I'm going to have 1 liter of oxygen. If I have 1 liter of oxygen, then there's going to be a lot more empty space here. We're going to spread out these oxygens over a bigger volume here. What do you think is going to happen to the pressure? It's going to go down because I'm going to have a lot fewer collisions because now there are no more blues in here colliding with the wall. Do you know what the pressure is going to be? It's going to be actually 0.21 atmospheres. It's going to be 21%. I have 21% of the particles hitting the wall. I'm only going to generate 21% of the pressure. So I have that. And then what I'm going to do is I'm going to put the nitrogen in a 1 liter. And so if I have 1 liter of nitrogen, I'll go through the boxes now. Just pour it on. Again, there's no red here. And so we're going to be missing 21% of the collisions. If we're missing 21% of the collisions, what's the pressure going to be? 0.79 atmospheres. And so this is what we call constant volume. When we look at our original mixture here, we can just visualize this using Dalton's easily. We can visualize this using Dalton's because what is the pressure generated by the red collisions and what is the pressure generated by the blue collisions? What we see is the pressure generated by both the red and the blue. If we're to separate it out into red only and the blue only, then that's what we're going to get over there. Because over here, when we look at this, we have 1 liter of oxygen that is free to roam anywhere it wants in the 1 liter. Nitrogen is free to roam anywhere it wants in 1 liter. And so this, compared to the Dalton's, just seems to make sense. You know, with Avogadro's, we'd have to separate this into two smaller boxes. Does that make sense? Yeah. So we'll take a look at these reactions here and see what we got.
Professor?
Do some gases liquefy at different pressures?
The liquefied, like for example, you could try to liquefy things at room temperature, like just generating high pressures. We're going to look at solids and liquids and gases in the next chapter. We'll talk more about it then. So if we have, let's say we have 1 liter of hydrogen here, and we're looking at the reaction, hydrogen gas plus chlorine gas yields 2 HCl gas. And so we can just use Avogadro's law for this. If I have 1 liter of hydrogen, how much chlorine do I need to react this? 1 liter. And the constraint with Avogadro's is it has to be at the same pressure. So if I look at chlorine, chlorine's usually green. No. If I wanted the same pressure, we'll have to have the same number of particles in 1 liter. So I do this. And this is going to make HCl, but I'm going to have twice as many HCl particles, so I'll need a bigger container for that. The HCl, the product. Because I want to maintain the same pressure, so I'm going to have 1 liter. If I try to force the HCl into 1 liter, then I'm compressing twice as many particles. I'm going to double the pressure. And so in order to maintain the same pressure, this has got to go to 2 liters here. That's what they're showing over here. In the first one. These are all under constant pressure, so this is Avogadro's. Dalton's is under constant volume. And so, constant pressure. Avogadro's. Dalton's, what I do is everything's in the same 1 liter. So what I'm going to do is I'm going to take 1 liter here. In the 1 liter, I'm going to put everything in there. The hydrogen and the chlorine. If this were 1 atmosphere, let's say this is 1 atmosphere here, then do you know what the pressure here would be? If I doubled the number of particles in the box. Yeah, it would be 2 atmospheres. So this is 2 atmospheres. But that 2 atmospheres consists of 2 things. It consists of the pressure of the hydrogen. You know, so if I just look at the red particles hitting the walls, that's going to generate the pressure. How much pressure will that generate? That will generate actually 1 atmosphere. It's the same. So this is 1 atmosphere of hydrogen. And then in that same container, I have chlorine. And so I have to add to that the pressure that's generated when the chlorine molecules hit the wall. And that pressure is going to be 1 atmosphere. So I have 1 atmosphere of hydrogen hitting the wall and 1 atmosphere of chlorine hitting the wall, giving me a total pressure of 2 atmospheres. So this is called P total. And the hydrogen and the chlorine are going to react to make HCl. And in 1 liter, P total here is going to equal, well, it's going to equal, do you know how many atmospheres it's going to be? It's going to be 2 atmospheres. And the pressure is just generated by the HCl only. There's nothing else. So when we do things under Daltons, the pressure changes depending on how many particles we put in the volume. Yeah. Sometimes the P total will change as well. If P total changes, then we need very strong walls. So for example, if P total increases, we don't want it to explode. If P total decreases, we don't want it to implode. So when we're doing things under Daltons, under constant volume, we have to make sure that the container can withstand significant drops in pressure or significant increases in pressure. And so usually it's done in a heavy walled steel container. Sometimes people call it the bomb. They do it in a bomb because it could potentially be a bomb. It would explode. And so in this case, the pressure didn't change, but in other cases it could. Whereas when we do things by Avogadro, the pressure's not going to change. We maintain things, so we need two separate containers, one container of hydrogen, one container of chlorine, and then we put these two containers together. Usually what we have is a variable volume container. So what are they doing here? In this case, they have excess hydrogen, and so there's some excess hydrogen remaining here. I don't know what else they're trying to show. Oh, they're showing that the volume doesn't quite match. Well, the volume doesn't quite match because this is not Avogadro. This last one is kind of a mix of Avogadros and Daltons. If you have twice as much hydrogen, this container should be twice as big. And so to correct this, C is wrong. If we did C in terms of Avogadros, then our hydrogen should be twice as big. So this is going to be 2 liters of hydrogen plus 1 liter of oxygen. What is this going to make? This is going to make 3 liters of product. The product is going to consist of 2 liters of HCl plus 1 liter of leftover hydrogen. That's the way it should have been drawn. Or just ignore this. I'm not sure what they're trying to do for this particular one. But what they're doing is a mix of Daltons, and we don't like to mix. You know, you either look at one from the perspective of Dalton, and then you look at it from the perspective of Avogadro. But we don't look at it from the perspective of Avogadros and Daltons at the same time. We do one at a time. It's not that in Chem 1A we do a lab where we look at a mixture, and first we look at it from a Dalton's perspective, and then we look at this exact same mixture from Avogadro's perspective. All right, that's gas mixtures. Now we're going to talk about the ideal gas law. This can be a mixture or pure, doesn't matter. We use the ideal gas law for anything. PV over NT is equal to a constant. And this constant we call R, the gas constant. And so the pressure we like to put in atmospheres. The volume in liters, N should be in moles, T should be in Kelvin. And then R will be 0.08206 liters times atmosphere per mole Kelvin. That's the gas constant. This is to 4 sig figs. Your book has it to 3 sig figs. To 3 sig figs, it's 0.0821. But in Chem 1A, you need to know it to 4 sig figs. So might as well just memorize it to 4. Actually, this is a number that people don't really have to work hard to memorize because you use it so many times. It puts it in the calculator. So as long as you do these types of calculations, it's not a hard number to remember. If you do forget, that's all right. This one you don't really have to memorize. I'll give it to you. So don't worry about memorizing. Most people do memorize it.
So is that by definition?
No.
No.
This is what's only. It would be infinite sig figs or by definition. All they do is they put in experimental values here and calculate it. When they put the experimental values for gas, they take a helium gas sample, put it in pressure, volume, the amount, and temperature, we get this number. If you an oxygen gas sample, we do the same. Air gas sample, we do the same. They always come up with the same number. This is why we came up with the equation P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. So P initial, etc., is equal to P final, etc. And so there are 2 equations you want to know. You want to know this equation, and then we're going to rearrange this equation. We rearrange this equation, PV equals nRT. This equation. This is called the ideal gas law. And that's over here, the ideal gas law. Ideal gas law is very useful. Fortunately, the basic calculation is not too bad. The ideal gas law is based on a combination of simple gas laws, Boyle's law, Charles' law, Avogadro's law. You don't have to know this. What we want to know is how to do a calculation. So typical calculation is, you know what R is, it's a given. And so all you need to know is 3 of these quantities to figure out the 4th. And so that's a typical ideal gas law calculation. 3 of the quantities are given, solve for the 4th. So a 0.592 mole sample of helium, figure 14-8, was found to occupy 14.7 liters when measured at 12 degrees C and 0.942 atmospheres. So they give us the moles, N. They give us V, the volume. They give us the T, the temperature, and they give us the pressure, P. So if we know the moles, the volume, temperature, and the pressure, then the only thing missing is R. And so in this one, they just want us to calculate what R is. So solve the ideal gas law for R. And so that's why I would say wanted R. Well, we already know what R is, but let's see how it compares. So they use the N as is because it's in the right units. V is in the right units. T is not in the right units. So they convert the temperature into Kelvin. P is in the correct units, atmosphere. And so when we plug this all in, we can calculate R. And so P times V, 0.942 atmospheres times 14.7 liters divided by NT. N is 0.592 moles. I wouldn't do it like this. I just put it all in one thing. I don't know why they ran 2 steps like this. And even this is weird. If I'm solving this for R, then we've got the equation. R is equal to PV over NT. And just plug everything in, 0.942 atmosphere times the volume, 14.7 liters, divided by the moles, 0.592 moles, and the temperature, 295 Kelvin. So the units would be liters atmosphere per mole Kelvin. And let's see, did they get right on 0.0821? Let me calculate that. And so we have 0.942 times 14.7 divided by 592 divided by 295. Wow, I didn't get anything close. I'm trying again. 0.942 times 14.7 divided by 0.592 divided by 295. 285. Oh, 285. Oh, actually, there's too bad, but it's not the whole thing. It says 285 in your book. Here it says 295. You know that's wrong. It is 285. I was just using that. So. 285. I guess they corrected it in your book. And it's wrong in my book. What did it come out to? 0.0820 Okay, it's supposed to be 0.08206, so there's some experimental error, slightly off. But if you do this for a whole bunch and then average it, that's what you come out as the average. You want to do thousands and thousands of these to get a decent average. Right? Close. And so the units are really important. Liters, atmosphere per mole Kelvin. Now, how many R's do you want to memorize? Well, or use? What we do is we just use one R value and convert everything to the right units. Your book doesn't do. Your book has different R values. So, for example, your book will have an R value if you use, bar instead of atmospheres. Well, it's easier just to convert bars into atmospheres and just use the same R. So I always just use the same R value. And so let's see the R values here. Okay, here's the same problem, I think. 656 milliliters. So that's the wrong unit. It should be in liters. 839 torr is the wrong liter. That should be in atmosphere. But where your book is going to go is, okay, let's just use a new R value with liters torr per mole Kelvin. Do you want to use a lot of different R values depending on what units? No. And so you'll see this R value a lot in our book because they use this one. The R value that we come up with is here, 62.4. So they're asking you to memorize two different ones, 0.821 and 62.4. Is that even? It seems ridiculous to me. Why bother memorizing 62.4 torr times liters divided by mole Kelvin? It's ridiculous because, if you have too many R values, because what do you do when you have, not torr, but what do you do when you have bar? If you have bar, that gives you a third R value to remember. Etc. So this problem I'll just skip. So that was an example of the ideal gas equation determination of a single variable. And so single variable calculations are pretty straightforward. So here, what volume? So volume's unknown. We have moles, we have atmospheres, and we have temperature. So we just need three of the four R we know already. And then we can solve. So solving this for V equals nRT divided by P. So that's what we have here. V is equal to nRT over P. And then they string it out like this. I think they string it out like this because of how you key it in your calculator maybe, but I don't usually do that. And so they solve for volume. All right. So There are other applications, and there are two different ways you can approach it. So let's look at the calculations. Ideal gas law calculations. The first one's easy. Solve for one unknown. Normally we want the pressure, the volume, the amount, and the temperature. So we just solve for one given the other three. Molar mass determination. We can use ideal gas law to calculate the molar mass based on experimental. So the molar mass of the gas is equal to the grams, or the mass of gas in grams, divided by the grams per mole, divided by the mole of gas, N. So we're going to have to be given how much the gas weighs. N of the gas, there's no mole meter. And so what we do is we're going to have to calculate N using the ideal gas law. And N is just equal to PV over RT. And what we do is we substitute that in here. So it's going to be the mass divided by PV over RT. And then I'm going to divide by fraction, so I'm going to convert and multiply. So this is going to be the mass times RT over PV. So this is one equation that we can use for this. The molar mass of the gas is equal to mass times RT over PV. This is kind of the equation. They wrote it in this form. Let's take a look at this problem here. A researcher vaporizes 1.67 grams of a liquid. And so they vaporize it means they convert that liquid into a gas. At a temperature of 125 degrees C, its volume is 0.421 liters at 749 torr. Calculate its molar mass. So I just use this equation here. The molar mass is equal to the mass times RT over PV. One could derive, this is a derivation of the molar mass equation, or one can use dimensional analysis to figure it out, because what should the units be? So let's say you forgot this equation, but you need to know the units of molar mass are grams per mole. And so if you look at the mass is going to be in grams. R is going to be in liters times atmosphere per mole Kelvin. T is going to be in Kelvin, divided by P, which is going to be in atmosphere, divided by V, which is going to be in liters. And so one way you can check this equation to make sure it's correct is by dimensional analysis. That is, the liters cancel out, the atmospheres cancel out, and the kelvins cancel out. And what does that leave me? That leaves me with grams per mole. That's what we want. If it doesn't come out to grams per mole, then just move things around until it comes out to grams per mole. So you can just kind of guess what the equation is and then just check it, guess and check, keep guessing and checking until it comes out right. That's another way. And so, one, you can derive it. Two, you can just use dimensional analysis, guess and check the equation. Or three, you can just memorize it. All right, so what we need here in this example is the mass of the gas, when they weighed it 1.67 grams. Then we need the temperature, 120 R 0.08206 liters times atmosphere per mole Kelvin. Then we need the temperature, but the temperature has to be in Kelvin, so it's 125 degrees, or just 125 to 273 Kelvin. And then we need the pressure. The pressure they gave us is 749 torr. So I go 749 torr here. And then the conversion is 1 atmosphere for every 760 torr. And then we want the volume in liters, which they gave it to us in liters, fortunately, 0.421 liters. And then just make sure the units work out. So the liters cancel. The atmospheres cancel, the torr cancels, Kelvin cancels, and that leaves us a grams per mole. And so we punch this out, and then I'll do that. $132 grams per mole. That's a heavy gas. That's why it was a liquid. Well, it's not, it's not because it's heavy that it's a liquid. It must have strong intermolecular forces. That is, they're kind of sticky molecules. So 132 grams per mole. So that's what I would do. What they did was they used this other R. Yeah. And converted to Kelvin. They did a check. They like to do these checks, that is, just look at it and see if that ballpark the right order of magnitude. So doing a check, 2 times this divided by that. You kind of do it in your head. And usually what I do is I forego this check and just punch it in my calculator again as a check. Make sure. All right, that's molar mass. The third kind of calculation we're going to do is density. Of gas. Let's see what symbol they use. The symbol for density varies depending on the book. So not all books use the same symbol for density. Our book uses capital D. This isn't so common. Most people use a lowercase d or Greek symbol for rho. We'll use the books. This is just for gas. The density of gas is equal to the mass over volume. Mass to volume ratio. That would be the density. So we're going to do this in the same way that we did the last one. What we're going to do is we're going to solve the ideal gas law for volume. So volume is equal to nRT over P. And then we're going to substitute that up here. So we're going to get the mass divided by nRT over P. And then we're going to invert and multiply. And so this is going to be the mass times the pressure divided by nRT. All right. We saw this before, mass over n. Where did we see that before? Mass over n. Yeah, that's the molar mass. Mass over n is the molar mass. And so this is the molar mass. Well, if that's the molar mass, then what we're going to do is we're going to simplify this equation. This is going to be the molar mass, mm, times the pressure over nRT. Oh, no, n. So over RT. So it's the molar mass times pressure over RT. This is a very powerful equation because with this equation, we don't even have to take any measurements. Like in the last example, they had to take measurements. They had to weigh it. They had to measure its temperature. its pressure, and its volume. That's a lot of work. In this equation, we don't have to do anything. All we have to know is what the gas is. So the density of the gas is equal to the molar mass times P over RT. So you pick any gas, like helium gas. We know the molar mass of helium gas. Helium gas is 4 grams per mole. What is it? 4.002. Oh, we should get more quickly. We'll just do 4.00 grams per mole. So if we know the molar mass, then choose any temperature and pressure. And we can calculate the density. So let's do this as an example. We'll choose room temperature and room pressure. So it would be 1 atmosphere. And so what is the density of helium gas at, well, it's 4.00 grams per mole times the pressure, well, that's 1 atmosphere. Let's just say exactly 1 atmosphere, divided by R, 0.08206 liters times atmosphere, divided by mole times Kelvin, divided by T. Room temperature is 298 Kelvin. And so what is the density of helium? Room temperature and 1 atmosphere pressure. So we do 4 divided by 0.08206 divided by 298. 0.16. Unit should be grams per liter. And so the moles cancel, the Kelvin cancels, atmosphere cancels, that leaves us with grams per liter. Okay, if we compare this to air, air is about over 1 gram per liter. And so helium is quite a bit, less dense, about 10 times less dense than air. For air, we use the average molar mass. Let's see if we have air in here. Calculate the density of nitrogen at 0.632 atmosphere and 44 degrees. First is it N or N2? If they say nitrogen. It's going to be N2. So it's 2 nitrogen. 2 nitrogens, each one's 1401, so that gives us 2802 for the molar mass of N2. And we'll just plug that in here. And we get the density of nitrogen. The density of it's 0.68 grams per liter. Determine the density of oxygen. What was the pressure? This one. The pressure was low, 0.632 atmospheres, and the temperature was high. A little bit low, but high. Okay, let me do a more complicated one. Density of a gas mixture. Let's do air. Air, we said, was what percent? 21% oxygen by mole. Typically, this is the way we write it. And 79% nitrogen. And so the first thing is, what we're going to do is, what is the molar mass of air? And what we're going to do is we're just going to approximate what the molar mass of air is going to be. So the way we do this is similar to doing atomic masses. 21 out of 100 parts will be oxygen. How much does oxygen weigh? So 16 times 2, which would be 32.00 grams per mole. Plus 79 out of 100 parts will be nitrogen. Nitrogen weighs less. It's only 28.02 grams per mole. And so this is going to give us what the average or what the estimated molar mass of air is. And so it's going to be, let's say 0.21 times 32 plus 0.79 times 22. The average molar mass of air comes out to 28.855 grams per mole. Yeah. There's other stuff in air that's heavier. I mean, this is for dry air. There's no water. You know, there's humidity in there. This can change it, but keep things simple. We'll do that. And so the density of air we're going to approximate as, okay, so molar mass 28.855 grams per mole. The density of air was equal to molar mass times P. We're going to do 1 atmosphere divided by RT, 0.08206 meters times atmosphere per mole Kelvin times T. We're going to do room temperature, 298 Kelvin. And so let's just make sure the units cancel. So moles cancel, atmospheres cancel, Kelvin cancels, gives us grams per liter. If I didn't get grams per liter, then I just play around until I get grams per liter for this. So I'll just leave this in my calculator, divided by 0.08206 divided by 298. So I get 1.180 grams per liter. And so air has a density of around 1 gram per liter, and helium has a density of about 0.1 grams per liter because helium particles, molecules, the helium doesn't form molecules. Helium atoms only weigh 4 versus air, which weighs about 28 each particle. So particles in the air are a lot heavier. It gives you a higher density. And for a given volume at the same temperature and pressure, we're going to have the same number of particles. Of course, if we change the pressure and the temperature, if we increase the pressure, it makes things more dense. If we decrease the pressure, it makes things less dense. If we increase the temperature, it makes it less dense. If we decrease the temperature, it makes it more dense usually. Determination of molar mass and density in the ideal gas equation. We can use density and molar mass. So molar mass and density of the gas. This only works for gases. The molar mass equation is molar mass is equal to mass times RT over PV. Does that look right? Well, we could use the units here, figure out the units. Make it look right. But do you recognize this? Mass over volume? What's mass over volume? It's the density. And so one variation of this is we can just substitute density in that. So this is equal to the density times RT over P. So we get this third equation. Third equation, we don't necessarily need, because if you know the density, let's say if the density were 0.618 grams per liter, then you just plug that in, 0.618 grams here and 1 liter here. So we really don't need this equation. It's redundant. But some people prefer to have a third equation like this. So here you just plug that in. What's that, 4? Number 5 is calculating molar volume of a gas. The molar volume we could have of gases and of liquids, whatever we want. The molar volume we're going to call MV for molar volume. And this is going to be the volume per mole, liters per mole of a gas. And we do the same thing as we did before. The denominator here is N. And so N is equal to PV over RT. And then we'll substitute that here. So just the denominator. This is going to be volume over PV. Did I do that right? Over RT. I guess I did. Okay. So I'm going to invert and multiply. So if I invert the volume actually cancels, so we just do 1 on top, and then I'll put RT over P. And so the molar volume is equal to RT over P. And so I don't even need to know what the gas, this is the molar volume for any gas, for any ideal gas. RT over P. Density changes, but the volume per mole. So 1 mole of any gas will have the same volume. And the same number of particles. It's out here. This is a molar volume at STP, 22.7 liters. I memorized a number very similar to this. This is the molar volume of 1 bar in 0 degrees C. So let's talk about STP. STP stands for standard temperature and pressure. Of a gas. Standard temperature turns out to be 0 degrees C or 273 Kelvin. Standard pressure is 1 bar. This is or 1 atmosphere. 1 atmosphere is old. This is new. So I've memorized this number, 23.4. Have you heard of that number, 23.4? Volume of the gas at STP. So 22.4. I actually forgot it. Wow. You know, it's good I forgot it. Because I had memorized this, like when I was taking, oh yeah, I had memorized this way back, probably in high school. I memorized this number. Then I memorized it again, you know, taking like Chem 4, Chem 1A, 1B. You know how many times I used it? 0. Pretty much 0. I never used it. I never used it because it's at 0 degrees C. How often do you do chemistry at 0 degrees C? Never. That's why I never used it. But I had memorized it. I had memorized it for decades. I knew this number. I wanted to get rid of it out of my mind because I wanted to make room for other stuff to memorize. Yeah, I guess my memory is gone. I have this completely memorized. Well, do you want to memorize this number? 22.7. I'm sure instructors are making students memorize it. 22.7 liters, just like I had. This is a quantity to memorize. 22.7 liter box here. I don't know. Maybe that's one of the reasons I don't like the homework set in this chapter. I don't like the homework set because they do way too many STP problems. So in some gas, let me take that. In some gas catalogs, they'll put the STP volume. It's all right. But it's an easy enough number to calculate. You don't need to memorize it. And so I wouldn't bother memorizing it. This is not a quantity to memorize. There's something more useful to memorize. Load it now. This conversion factor provides you with a one-step conversion factor of making the macroscopic volume of gas at 0 degrees C and 1 bar and the particulate level, number of particles grouped in mole. And so this would be 6.022 times 10 to the 23rd particles in that box. And if that were at 0 degrees C, it would occupy 22.7 liters. The 22.7 liters per mole is the mu, and 22.4 liters per mole is the old. Maybe on some standardized tests they might ask you. This is a more useful number to memorize. You're going to memorize one. That is the pressure, 1 atmosphere, but the temperature not 0. The temperature at 25 degrees C, which is room temperature. What is the volume of a gas at 1 atmosphere at 25 degrees C? And so we calculated the molar volume of the gas is equal to RT over P. R 0.08206 liters times atmosphere per mole Kelvin. T is 298 Kelvin. And P is 1 atmosphere. So what does the molar volume come out to here? 0.08206 times 298. 24.453 liters per mole. Or to 3 sig figs, we'll just do 24.5 liters per mole to 3 sig figs. To more sig figs, I probably should have done not 298, but I probably should have done 298.1. What is it? 298.15. 0.08206 times 298.18. Yeah, about there. So we'll just leave it 24.5, 24.5 liters. All right, let's stop here and we'll take a break. Start again. Video I was talking about, how to easily learn difficult things. So just more tips. We'll just look at the intro to this, and if you're interested, you can check it out. At the UC's, the lab is a separate class. So the lab is a 1 unit course entirely separate from lecture. UCs, they don't generally collect homework. You can do it if you want. It's up to you. Most people do it. Or maybe not. Maybe you won't watch it. Audio.
Applications. That's what I decided to do. As between sometimes shitty lectures, council teaching, and worldwide global events, a lot of this learning has not actually happened in the lecture theatre or in education. Imagine what would happen if you suddenly decided to become a doctor. You spend the next 7 to 8 years having to absorb endless information on human anatomy, physiology, pharmacology, behavior, communication, alongside skills and applications all into your brain. That's what I decided to do. And between sometimes shitty lectures, council teaching, and worldwide global events, a lot of this learning has not actually happened in the lecture theatre or in hospital, but it has had to be self-taught. So, as any other medical student, I have spent a significant proportion of my 20s just learning. And the single most life-changing skill I have taught myself is how to teach myself. So today, I thought I would completely break down and show you the step-by-step process that I use to teach myself, especially very difficult topics to learn, in a way that makes them digestible, memorable, and above all, applicable and interesting. This will be a combination of my own personal experience, tips that I've gained from reading the books of the most excellent teachers in the world, and also a bunch of evidence-based research around the human memory, brain, and learning. Let's get straight into it. There was this general consensus that neurology is a very difficult topic to study, so for the purpose of this video, I am going to break down how I would study one topic in neurology, which is multiple sclerosis. So I have a 6-step process, of which the very first step is called broadening the context. And what I will be doing here is placing this topic in a broader context in the world and in my brain for it to make sense. Because at the moment, multiple sclerosis is just a chapter in a textbook or some questions in my exam. I don't particularly care about this. There's many chapters in many textbooks. There's no inherent curiosity in me to go, oh my God, I must know what this is about. And before you say, well, you spend a lot of money in university and if you don't study properly, then you're not going to pass your exams, this is not enough incentive for me to actually study things properly or care about the things that I study. So I need to place this in a broader context in order for it to make more sense and excite me a bit more. Words in a textbook, not exciting. Real life world, much more exciting. Richard Feynman, one of the best teachers in the world, identified this phenomenon when he said, I have to understand the world, you see. So he felt very, very strongly that people have an inherent curiosity about how things in the world work. And this is what I try to leverage. Before I study anything that is difficult, I need to put my curiosity about this topic and my emotional investment in this topic at the maximum level it can reach. And at the moment, it's just non-existent. Multiple sclerosis, couldn't care less. So let's make it very interesting for Elizabeth. Now, the way that I will do this is that I will go to Google and I will Google multiple sclerosis and I will go to the news tab. But what I'm looking here is for some sort of media case. This is not going to be the studies of new drugs being found because again, I'm just not interested in this enough at the moment. This will be, is there some celebrity who has it? Is there someone who died because of it? Is there some huge controversy around this? Because I know that my brain is much more likely to kind of attach to these interesting things than it's to attach to a list of molecules with
a house or a laptop? Which one do you think is worth more? Definitely not the house, because it not only costs millions to buy, but
which I don't kind of recognize at the moment. So still, there's no textbook here. I'm just on Google and I am searching for something related to multiple sclerosis. And what I found, this is going to work perfectly. So this is a Guardian piece on Selma Blair discussing her history with multiple sclerosis. Ideal, absolutely ideal. I don't know who this lady is, but she looks like she's famous. So this is a famous person that I can identify the disease with. And what I'm going to do at this stage is that I am going to kind of read this and place it in my mind. If I just read about multiple sclerosis in a book, there's nothing that can connect it to pre-existing things in my mind because there's no slot for multiple sclerosis in my mind at the moment. There's something around neurology, and yes, I can identify facts here and there, but if I'm just treating every single chapter as just random facts, they're all going to kind of disconnect at some point and not make any sense. So what I'm leveraging instead of my random science fact is I'm leveraging my curiosity and my understanding of the world in a much more layman sort of way, in a way that anyone would understand. And if this is written on The Guardian, I'm absolutely sure that everyone will understand. While I'm reading this, I'm going to be picking out things that stand out to me that I know that I can anchor to. Now, what anchoring is connecting things from my pre-existing strong memory to things that are specific to multiple sclerosis. And I want this connection to be as strong as possible. So therefore, this context is really, really strong. So let's have a look. She's describing her childhood. I'm going to be picturing her every time that I read these things. So it says that she suffered from multiple symptoms that come and go. Okay, so this is very interesting. There's a bit here about her going to Florida on a holiday. And this is interesting because it's Florida specifically, which is really warm. I can remember that. And then she was a trip for Instagram, so paid influencer thing. She bought a tiny bikini and an Hermes shoes. Okay, very fancy. So they're on a yacht. Again, really strong imagery here going on in my mind. And what happened here was, unfortunately, when she was on the water, she couldn't move. Okay, so she jumped off the yacht and then she was kind of paralyzed. She thought she was paralyzed. She couldn't control her limbs. She couldn't swim in the water. Okay, this is a very strong visual experience for me. Someone in kind of a tiny bikini and in Hermes shoes jumping off the boat. She probably didn't have the shoes on, but in my mind, jumping off the boat into the sea, cannot move. Okay, this is very strong imagery. Good. So then we move on. So what happens is that, yep, she had a Romberg's test. Okay. She ordered an MRI on the spot. She talks a lot about how no one had ordered her MRIs in the past. Okay. Oh, again, very, very good. There's a part where she speaks about using a cane at a celebrity event, which again is something quite rare that we don't get to see. She was crying quite a lot, unfortunately. Oh, bless her. Interesting. There are times when, okay, so there's times when both the dog pees in the house and she pees herself because she can't, so she probably has some urinary incontinence here. Okay, interesting. There's a lot of visual stuff here. Okay, so there was a lot of information here related to multiple sclerosis, which is probably quite similar to the list of symptoms I would be getting in a textbook. But in this case, they are being anchored to so many things in my brain. So I'm thinking yachts, I'm thinking Salma Blair, I'm thinking canes, I'm thinking dogs, I'm thinking peeing one's trousers, I'm thinking not being, sometimes dancing, sometimes not being able to move. So there's all of these things. I'm building a very strong picture in my mind and I'm anchoring it specifically to this individual. So thank her so much for writing this article. I think there's a book of this somewhere. So this has meant that I've put this neurological condition into context. Now I'm going to be focusing on step number 2, which has to do with emotional implications. And what this means is that if there is a very, very challenging topic, I need to make sure that I am fully emotionally primed to tackle this. And what this means is that I need to understand the consequences of not learning it and understand the benefits of learning it, and also try to convince myself or try to frame it in a way that I am genuinely itching to do this. This is the dopamine section of this study method. Dopamine is a neurotransmitter which is related to our anticipation of something. When we are anticipating something exciting, dopamine increases in our brain and we really, really want to do this thing. So this is what I'm trying to do with these sort of topics. So at the moment, yes, I'm slightly interested in her story, but again, there's many stories out there. Why would I specifically want to learn about multiple sclerosis? So because we know that the scarcest interest is desire, we want to go for the desire angle here. So I'm going to go back to the article and see what is something interesting here. What is something about future me that might be interesting? Is there something that particularly might make me kind of compelled to learn more? So okay, I think the part that stands out to me the most was she's been misdiagnosed her whole life, and especially there's this segment when she said, or when she got diagnosed, she said she felt an adrenaline rush of emotion. It felt like giving birth, the release of it. And I've gone through this myself. When you get a diagnosis for something that you've had your whole life and you suddenly understand what that thing is, it can be so absolutely relieving and life-changing. And it's such a bittersweet but mostly sweet moments. And I can really relate to her with this thing. And so I don't have multiple sclerosis, but I can see how she must have felt in some ways, in some capacity, with her experience. So now I'm emotionally invested. Now I know that this is one of those conditions that sometimes gets missed, that sometimes is misdiagnosed, that apparently some very few tests could have found. So for her, it was a positive Romberg's test and an MRI. So now I'm kind of frustrated and emotionally invested. Yes, I need to understand what the hell is happening here and why this is so important. I hope you can see at this point how I have a very, very vague clue about what this condition is, but I'm already much more likely to remember details about it, and also I'm much more likely to be emotionally invested in this topic. A huge neurology topic, which is just in the chapter in my book, I could not have cared less about. Now I'm like, hell yes, this is absolutely awful. Let's learn about it. Let's study more. So now I get into part 3 of my study, which is the deep dive, and this is potentially the most controversial bit.
Okay, well, if you want, I'll post a link if that's, that might be helpful enough. see. Um, actually, I'm going to continue on with the chapter here.
Will there be a study guide for the final?
Just review.
Just to review.
Okay, we're going to look at gas stoichiometry next. This stoichiometry involving gases. Your book has it divided into two different sections here. 14.7, gas stoichiometry at standard temperature and pressure, STP. This is why they want you to memorize this. They want you to memorize 22.7 liters per mole, because that will help a lot if you're doing gas stoichiometry at STP. The other is if we're doing gas stoichiometry at temperatures other than, pressures other than STP. And so it's 14.8. Take a look at that. Actually, that was 14.8. This will be the next one. And so they have three sections here. What we're going to do is we'll just go back to stoichiometry map. The stoichiometry map just has grams of A, or mass of A, to moles of A, to moles of B, to grams of B. This is our standard stoichiometry map. This is your standard stoichiometry value. Now, if we have a gas, measuring the mass of the gas isn't so easy. It's a bit of a pain to measure how much the gas weighs. And so measuring the mass of A is not so easy. Instead, what we might do is measure the volume of A. And typically, that's what's done. We measure the volume of A, and A is a gas. So the volume measurement's a lot easier. Now, we have different ways we can approach this. One, if we do this at STP, then we know there are 22.7 liters per mole. And so we could flip this over and use that as a conversion factor. That is, 1 mole of gas occupies 22.7 liters. That's one way. That's standard temperature and pressure. Or we could do RTP. RTP would be room temperature. What's room temperature? 25 degrees C. Pressure would be 1 atmosphere. This is STP in bar. This is RTP in atmospheres. And if I do RTP in atmospheres, how many liters per mole? 24.5. So we can use that as a conversion factor. It doesn't matter what the gas is. Any gas will be 24.5 liters in a mole. Or we could use the ideal gas law. If we use the ideal gas law, then we can calculate the moles. The mole N is equal to PV over RT. And we'll be solving for it. And that will take us to moles. So those are three different methods that we can use here. We can, actually really two. One is the molar volume, which the first two would be. Or what if it's not at RTP? I forgot to include that in here. Let me include that here, sorry. And then over here. If it's not at STP or RTP in atmospheres, then we calculate the molar volume. The molar volume is equal to PB, and what was the molar volume equal to? RT over P. Sometimes I forget, but if I forget, I'll just do this. I'll just figure out the units. R is in liters, atmosphere, per mole, Kelvin. T is in Kelvin, P is in atmosphere. So the atmospheres cancel, the Kelvin cancel, that gives us liters per mole. That's what we want. So it's RT over P. And so if it's not an STP in bar or RTP in atmospheres, then we just calculate the molar volume here. And so the first three methods involve molar volume. The last method just involves an algebraic calculation of N here. Okay, now if B is a gas, we can do the same thing. Typically, we want to know what is the volume of a B gas that forms here. So the volume of the B gas, we could do the same thing. That is, if it's at STP, then we'll just use 22.7 liters per mole. This is for bar. You don't have to memorize this number. If it's at RTP, this is for bar. If it's RTP, room temperature pressure in atmospheres, then it's 24.5 liters per mole. If it's neither of those, then we'll use the molar volume equation and calculate it. Molar volume is equal to RT over P. Or we could use the ideal gas law to calculate it. The ideal gas law says that the volume of B gas is just equal to nRT over P. The other way we could do it is we could use Avogadro's and go directly volume to volume. But there's one constraint here. If we use Avogadro's law, then the pressure and temperature must be the same. That is constant. And so the temperature and pressure can't change in going from, let's say you measure A at one temperature and B at a different temperature. But if we do Avogadro's law, then remember that the moles is directly proportional to volume. And so the balanced chemical equation gives us the mole ratio, which is the same as the volume ratio. So those are the methods that they talk about in the book. All right, so let's take a look at some problems and see which approach we want to take to the problem. This is the Avogadro's volume-to-volume gas stoichiometry, which is in the last section. So these are equations, calculations involving a single variable. Here's gas density. Here's molar volume. Here we have gas stoichiometry at STP. Then we have gas stoichiometry, the molar volume method, and gas stoichiometry, the ideal gas method. And so these aren't at STP. All right, so what we'll do is we're going to change this, number 29, since we don't typically work at STP. We work at room temperature. And so I'm going to change this. Number 29. We'll call it 29 modified. Find RTP. This is going to be atmosphere. Volume oxygen that can be produced by 5.74 grams of KClO3. What's KClO3 called? Yeah. This is an experiment with money where you take potassium chlorate and heat it out. When potassium chlorate's heated out, you take 2 KClO3 solids, a white solid. We add some catalyst to this to speed it up, but it decomposes into 2 KCl solid plus O2, 3O2 gas. So KClO3 is a solid, O2 is a gas. And so probably the best method is we're going to do the molar volume method with RTP. And so what we're going to do is we're going to go from grams of KClO3. Let's do it over here, 5.74 grams of KClO3. And we're going to convert that to moles of KClO3. Then we're going to go to moles of O2. And then from moles of O2, we're going to go to volume of O2 gas using the molar volume RTP. Molar volume is 24.5 liters per mole at 298 Kelvin in 1 atmosphere. So let's do that. The first thing is I need the molar mass of KClO3. I don't want to calculate it. I'm just going to look it up. So I'll look up KClO3 here. A molar mass is 122.55 grams per mole. All right, so I'm doing this calculation. We have 5.74 grams of KClO3, and then 1 mole of KClO3 weighs 122.55 grams. So I go from grams to moles. That's their standard stoichiometry first step. And then mole to mole. And so it's a 3:2 ratio. 3 moles of O2 for every 2 moles of KClO3. And so moles of KClO3 cancel. That leaves us with moles of O2. Well, O2 is a gas. And if we know the molar volume of the gas, then we can go ahead and calculate it. So under these conditions, the molar volume is 24.5 liters. It's bigger than 22.7 liters. For one, the temperature is higher, 0 degrees versus 25 degrees. 2, the pressure is actually a little bit higher. Atmosphere is a little bit higher. So it would be even bigger if this were a bar per mole. This is for any gas at RTP. That would be the restriction. And so what is the volume of the gas here? The volume of the gas, we calculate. .74 divided by 122.55 times 3 divided by 2 times 24.5. 1.721 liters. 1.721 liters of oxygen gas is produced from 5.74 grams of KClO3. All right, let's take a look at what they got. Here. Well, this is number 29. And they got 1.59 liters of O2. it's the same amount of oxygen, it's just at a lower temperature, and so it's going to be a little smaller volume. Okay, so 31 is similar. This is another potassium permanganate with HCl. This is how we generate chlorine gas in the lab. We take some potassium permanganate, which is a strong oxidizer, and we oxidize the chloride in hydrochloric acid. And it gets oxidized to chlorine gas. It's a redox reaction. We could use the chart method to figure this one out. This one looks like a double replacement, AB plus CE, but it's not a double replacement. It turns out to be a redox. Calculate the mass in grams of potassium permanganate that are needed to produce 9.81 liters of chlorine measured at STP. Taking a look at 31. This is going to be modified. We're going to just do it at RTP rather than STP. Since STP would be a very inconvenient temperature to work at. And so if we have 9.81 liters at 298 Kelvin and 1 atmosphere, and we know what the molar volume is, it's 1 mole of gas occupies 24.5 liters. So this is at RTP. At STP would be 1 mole of gas occupies 22.7 liters. And that would be RTP. We can do RTP at R2. It gives us a slightly bigger number. And it gives us the moles of oxygen. Once we have the moles of oxygen, then we're going to convert that to, or actually that's not, it's chlorine. Once we have the moles of chlorine, here it doesn't matter what the gas is. Any gas is going to have the same mole volume as long as it's ideal. Then we have the molar ratio here, and that is, it's going to be 2 moles of potassium permanganate, NaOH, for every 5 moles of chlorine. And then potassium permanganate, I don't know how to calculate that. Just look it up. Yeah. I mean, we could calculate this one. NaOH 158.03. So this is your typical stoichiometry with a number that you've memorized. And so this is a useful one to memorize. It's not necessary though. Memorize it if you would. What happens if it's not at that temperature and pressure? Then what do we do? So for example, if we look at number 33, it's at 983 torr, so it's slightly higher, and it's at a much higher temperature, 214 degrees C. So one source of sulfur dioxide used in making sulfuric acid comes from sulfide ores by the reaction 4FeS2. This is called pyrite, and has a weird anion on it, plus 11O2 yields 2 Fe2O3 and 8 SO2. How many liters of SO2 measured at 983 torr, 214 degrees C are produced by the reaction of 598 grams of FeS2? So we have a choice here. The choice is we can calculate the mole volume. I don't have the mole volume memorized for this. There's no reason to. But it's easy to calculate the mole volume, or we can use the ideal gas law to do this. We'll do it both ways. Let's see. So this is 598 grams of FeS2. FeS2 is pyrite, and it's iron with a 2+ charge, and then it's these sulfurs. These are called disulfide, which is S2, 2-. It's not one of the anions that you had to memorize. It's an ionic compound. It's just. And so people might think it's iron 4, but it's not actually iron 4. This is called fool's gold. When you see crystals of this, gold doesn't crystallize like this. And the density of this is a lot less than gold. Let's see what the density of fool's gold is. The density is 5 grams per cubic centimeter, approximately, or 5 grams per milliliter. You know what gold density is? 20, yeah. So gold is like 4 times more dense. And so it's easy to tell the difference between real gold and fool's gold. Yeah, it's another crystal. All right, so what can we need? We need to have the molar mass. All right. Here it is. Formula mass 119.98 grams per mole. And then I need to go back to the Balanced equation and do the mole. And it's 4 to 8. So 8 moles of SO2 for every 4 moles of FeS2. So that gives us moles. Now, moles of SO2, we have different choices. We can calculate the molar volume. So choice 1 is the molar volume method. Choice 2 is the ideal gas equation method. The ideal gas equation method would be V is equal to nRT over P. Okay, so we'll do 1 here initially. If I do 1, I need the molar volume. The molar volume of the gas is RT over P. R is just 0.08206 liters times atmosphere per mole Kelvin. T is, what is that, 214? It's going to be 214 plus 273 Kelvin. P is 983 torr. And 1 atmosphere contains 760 torr exactly. And so the units should work out. Atmosphere cancels, Kelvin cancels, torr cancels, and gives us liters per mole. That's what we want. So let's see what this comes out to. Point 0.0826. 0.08206. 487 times 487 divided by 983. times 760. 30.89 liters per mole. All right, so then I can use this as a conversion factor here, 30.89 liters per mole. This would be the molar volume. That will give us liters of SO2. So let's calculate it. It's 5.98. Divided by 119.98 times 8 divided by 4 times 30.8. 3.070 liters of SO2. All right, the other method is this. We need to calculate the moles of SO2 that we have from here. And so the moles of SO2 is where we're going to end up with. So this is going to be 5.98, or oops, not 598, sorry. 598, this is going to be 307 liters. That's what we got. That's what you got? Yeah. So the other method is 598 divided by 119.98 times 8 divided by 4, which is times 2. All right, the moles of SO2 is 9.968 moles of SO2. That is, stop the calculation here, and then solve for the volume. 9.968 moles times R, 0.08206 liters atmosphere per mole Kelvin, times T, which would be 487 Kelvin, divided by P, which is 983.4, and you convert that 1 atmosphere to 764. All right, so times 0.08206 times 487 divided by 983 times 760. 307.9. 307.99. So it's slightly different. The reason it's slightly different is because I rounded this here. I didn't use all the digits. And so I have some round off error there. But that's okay. All right, so those are the two ways that we can do it. We can either calculate the molar volume and use that as a conversion factor, or we can stop here and then do another algebraic calculation to figure out the volumes for this particular problem.
That's 487 Kelvin?
Yeah. All right, the volume here, we'll take a look at this. The third way of doing this is if we had two gases. But we don't have two gases here. One was a solid, the other was a gas. And so there were only two ways of doing this. The problem here. But number 41, sulfur burns to SO2 with a beautiful deep blue-purple flame, but with a foul, suffocating odor. And so sulfur burns in O2 to form SO2. Now sulfur is a solid, but O2 is a gas and SO2 is a gas. How many liters of O2 are needed to form 35.2 liters of SO2? So if we have 35.2 liters of SO2, we can use stoichiometry to go from liters of SO2 to moles of SO2, and then from moles of SO2 to moles of O2, and then from moles of O2 to liters of O2. When we go from liters to moles, we have two choices. One, we could use molar volume, or two, we could use ideal gas law. And the same thing here. One, we could use molar volume, or we could use the ideal gas law. Or two, we can just bypass this altogether. We can use Avogadro's law, or volume to volume. And that is, if we have 35.2 liters of SO2, then I know that for every 1 liter of O2, I need 1 liter of SO2 to form. And so the mole ratio, that is 1 mole of O2 for every 1 mole of SO2, is the same as the volume ratio. That is 1 liter of O2 requires 1. And so this one, we didn't have to do any. This is going to come out to 35.2 liters of O2. So we need 35.2 liters of O2 to react. Both gases being at the same pressure and temperature. So I don't even need to know. I just need to know that they're both at the same temperature and pressure, and then I can use the volume to volume conversion. This is the volume to volume conversion here. But they screw things up here in part B. In part B, it's all screwed up because what if only the SO2 is under those conditions, but the O2 is at 17 degrees C and 47 for. And so now we have two different conditions here. So what should you do? I'll tell you how the book's approach to this. This is the way I do it. These two gases are at different temperatures. So this is 41A. If you go to 41B, then we can't do the volume to volume because the temperature and pressure change. And so here I'm going to have 35.2 liters of SO2. Now there are different ways that you can approach this. I just do everything kind of the same way. And so what I need to do is I need to figure out how many moles of SO2. What's your preferred method? The molar volume method or the ideal gas equation method? Do you have a preferred one yet? Molar volume? Okay. If we do the molar volume method, then we need to calculate the molar volume. And so this is the molar volume of the SO2. The molar volume of SO2 is equal to RT over P. R is 0.08206 meters atmosphere per mole Kelvin. T is 26 degrees C. And so it's 299 Kelvin. T is 741 and so we'll convert that here. 741 torr, 1 atmosphere is exactly 760 torr. And so we do a quick calculation. That would be 0.08206 times 299 divided by 741 times 760. And that gives us 25.16. 25.16 liters per mole. Okay, so I'll do that here. I'm going to start off with 35.2 liters of SO2, and then for every mole of SO2, I'll have 25.16 liters. This is actually for any gas under these conditions, but I'm going to label it SO2 because the O2 is going to be under different conditions, so this one won't work for the O2. And then it's a 1-to-1 mole ratio. So 1 mole of O2 for every 1 mole of SO2. And then I have to get the molar volume for the O2. But the O2 is at 17 degrees C and 847 torr. From moles of SO2 to moles of O2, and from moles of O2 to liters of O2. But the O2 and the SO2 are under different conditions. And so over here, let's calculate the molar volume of the O2. Can you calculate the molar volume of O2? That's 17 degrees C and 847 torr. Let me know when you got it. 21.35. Is that what others got? Okay. So then we can put it here, 21.35 liters of O2 for every mole of O2. And that should give us the liters of O2. Okay. Let's see what we've got. So I do 35.2. Divided by 25.16 times 21.35. That gives us 29.86 liters of O2, or 29.9 liters of O2. Is that what you guys get? Okay, now the book does this a little differently. So we use the molar volume, and using the ideal gas law is fine, you can do it that way, but the book does something completely different. For this, which is 41, let's see what the book does. All right, the book, part A is fine. We just use the volume-to-volume conversion. It's a 1-to-1 mole ratio, so it'd be a 1-to-1 liter ratio. So 35.2 liters of SO2 and 35.2 liters of O2. What the book does is they use this equation first here. The equation here is that they convert the SO2 from one condition to another condition. So the book does this. This is what we just did. So the book goes with 35.2 liters of SO2. Under conditions 1. Conditions 1 was 299 Kelvin and 741 torr. And so they did 299 Kelvin, 741 torr. Well, that's what was given. And then what they do is they use the combined gas law to calculate the volume SO2 under the second set of conditions. And so they convert this to 29.9 liters of SO2. 29.9 liters of SO2. But the temperature and the pressure will be, what was the temperature and pressure for the oxygen? 290 what? 290 Kelvin and
1.114 atmosphere.
alright. And so what they did was they used this P1 V1 over T1 is equal to P2 V2 over T2. And they solve for V2. So this is V2. And then once they get the SO2 under the same conditions as the O2, they do a liter to liter conversion. And so they end up with 29.9 liters of O2. And so it's 1 liter of O2 for every 1 liter of SO2. And so that's what they're doing. I don't do it this way because I feel like just in the stoichiometry mindset, in the stoichiometry mindset, I do things stoichiometrically. And so I wouldn't do this like this, but it doesn't matter how you do it. You can do it this way, it's fine. All right, so those are all the types of problems that you'll encounter here for this chapter. Chapter 15, we're going to be looking at gases, liquids, and solids here. 15.1, I already talked about that, and that's Dalton mixture. And so let's take a look at 15.1. Here's where you're going to find Dalton. It's called Dalton's law of partial pressures. I think it's called Dalton's law. This is Dalton's law. Let's have a mixture of nitrogen and oxygen. This is 15.1. The mole fraction's always true. And so this head contains 0.0100 moles of N2 and 0.0050 moles of O2. So let's say you have a container. And this container has 0.0100 moles of N2 and 0.0050 moles of O2. So what is the mole fraction? The mole fraction of N2 is 0.0100 moles of N2 over the total. The total is going to be 0.0150. So 100 out of 150 is like what? Fraction? 2/3? Is that right? So 2/3 of mole N2. Or percentage-wise, it's 67% nitrogen. Let's just round it to 260, 66.6666, etc. The mole fraction of O2 is we're going to have 0.0050 moles of O2 for every 0.0150 moles of total, which is going to give us a mole fraction of 1/3, which is 33%, a mole. I forgot to write mole. 33% on the molar. So yeah, a container contains 67% nitrogen, 3% oxygen. So this is kind of like air, except the percentage is a little different. So 1/3 of this is oxygen, 2/3 of this is nitrogen. How much? We have 1 liter, and it's at 25 degrees C. Some pressure here. 1 liter, 25 degrees C, and the pressure is 279 millimeters of mercury. We're using the barometer. Is this a barometer? We're using a manometer to do that. This is a special manometer, though. This is what we call a closed-end manometer. Do you see, look at the top here? You see how it's sealed? In a closed-end manometer, we don't have air weighing down on top of this. If this were an open-end manometer like we had in the earlier chapter, then the weight on the left is equal to the weight on the right. The weight on the right is the pressure of the gas mixture. The weight on the left is the pressure of this liquid, which would be the height, 279, plus the pressure of the atmosphere. But since this is a closed-end manometer, we don't have to, there's no atmosphere inside here, this is a vacuum. And so the pressure is just 279 millimeters of mercury. So in Dalton's law, we visualize this mixture. How do we visualize this mixture? The way we visualize this mixture is how much nitrogen do we have? How much nitrogen do we have in terms of liters? How many liters of nitrogen? 0.67 liters would be for Avogadro's. For Dalton's, how many liters of nitrogen? 1 liter. And so we're going to have 1 liter, although I'm drawing it smaller because I'm going to draw something underneath it. We're going to have 1 liter of nitrogen. And we're going to remove all the oxygen. If we remove the oxygen, then we don't have the collisions of the oxygen contributing to it. And so what will the pressure be here? If we remove 33% of the molecules out of there, then the pressure is going to go down. Right? And the pressure will be, instead of 279 millimeters of mercury, it'll be 2/3 that pressure. Does that make sense? And so what is this pressure? So the pressure of the nitrogen is going to be equal to 2/3 the total pressure. Yeah, 186 millimeters of mercury. Well, that's what they got. Yeah. Okay, plus we're going to have 1 liter of oxygen. And the pressure of the oxygen is going to be 1/3 the total pressure. And that's going to be 93 millimeters of mercury. And so note this. 1 liter of nitrogen plus 1 liter of oxygen equals how many liters of mixture? So this is the way you got to think in terms of Dalton's law. If I take 1 liter of nitrogen plus 1 liter of oxygen, how many liters of mixture do we end up with?
2.
You think 2. This would be 1/3 pressure. And no, we don't end up with 2, we end up with 1. We have 1 liter of mixture. However, what happens with the pressure is if I take 186 millimeters of mercury of nitrogen plus 93 millimeters of mercury of oxygen, what's the pressure of the mixture going to be? The pressure of the mixture is going to equal the total pressure because now we have everything in the same box here. And so we have 1 liter, and the nitrogen's still there, exerting a pressure of 186. And then we have the oxygen's there, exerting a pressure of 93. And so P total is going to be what we say is the sum of the partial pressures. And the sum of the partial pressures is going to be equal to the pressure of the nitrogen plus the pressure of the oxygen. And so the pressure of nitrogen was 186 millimeters of mercury, and the pressure of the oxygen is 93 millimeters of mercury. And the total pressure will be 279 millimeters of mercury. This is the volume. So what they're saying is they're taking 1 liter plus 1 liter, that gives us 1 liter of mixture. What's going to happen? The pressure's got to go up. Then there's an error here because the volume changes. I mean, the volume here is not the same as the volume here, which is not the same as the volume here. So the volume's actually changing. This isn't very good because that's going to lead to an error. The volume's not 1 liter. It should be 1 liter throughout. What about Avogadro's? How would you describe this using Avogadro's?
Pressure would stay the same, but you change the volume.
Yes. And so here you would go, how many liters of nitrogen would you have?
0.6, 7.
Yeah. So over here we're going to have 0.67 liters of nitrogen. What's the pressure of the nitrogen? Yeah. The pressure of the nitrogen is going to be 279 millimeters of mercury. So 279 millimeters of mercury. Okay, plus how many liters of oxygen?
0.33.
Yeah. And so we're going to have 0.33 liters of oxygen. And what's the pressure of the oxygen? 279 millimeters of mercury. And this is going to produce how many liters of mixture?
1 liter.
Yeah. So 1 liter. And if I have 279 millimeters of nitrogen plus 279 millimeters of oxygen, how many millimeters of mercury of mixture will it have?
279.
Yeah, 279. And so we have a simple way of describing this. Dalton's is constant volume. Avogadro's is constant pressure. So under conditions of constant volume, the volume doesn't change. So we could add 1 liter plus 10 liters plus whatever. Actually, volume doesn't change. It has to be 1 liter plus 1 liter plus 1 liter is always going to give us 1 liter. And so the pressures are additive. So P total is equal to the sum of the partial pressures. The partial pressures are the pressures of the individual species or components of the mixture. Whereas in Avogadro's, the pressure doesn't change. The pressure is always the same. And so V total is equal to the sum of the partial volumes. And so if we were to understand this in terms of Avogadro's, this is the way we do it. The way we do it is nitrogen, we shrink down. You know, it's 1 liter, we shrink it down to 0.67 liters. If we shrunk the volume down to 0.67 liters, that'll bump up the pressure to 279 millimeters of mercury. And the oxygen, we shrink the volume down to 0.33 liters. And if we did that, then that would bump up the pressure to 279. So there are 279 plus 279. And then we add those up. 0.67 plus 0.33 is going to give us 1 liter. And then 279 gives us 279. And so we're just adding the two containers to one another. And that's how we do that. And so we talked about Avogadro's in chapter 14, and we talk about Dalton's in chapter 15. It's split this way. Here. But they should be talked about together because so it depends on how many gases you have in the mixture. In this case, we only have 2 gases, P1 and P2, nitrogen and oxygen. In other cases, we may have a lot more. And so here is a problem. If a gas mixture, in a gas mixture, the partial pressures of methane 154, ethane 178, propane 449. What is the total pressure? Well, the volume is going to be the same. All these, they're going to be in the same container essentially. And so we just add up, you know, collisions from ethane generate that much pressure, the collisions from propane, that much, and methane from that much. So we just add them up. So Dalton's law is really simple. Just add up the pressures to get the total pressure. Avogadro's is simple. It's just when you start comparing Avogadro's and Dalton's, that's when things get confusing and people get confused with this. A scientist sets up an artificial atmosphere with 4 gases. Their partial pressures are 0.78, 0.21, 0.00, 0.025 bar. Whenever you see different pressures like this is Dalton's. Just add them up to get the total pressure. In Avogadro's, the pressures will all be the same. 1 bar of nitrogen, 1 bar of oxygen, and the volumes will be different. Okay. In this KClO3 experiment that you do in Chem 1A, potassium chlorate, you take some white potassium chlorate and then add a trace amount that is a small little scoop of MnO2. MnO2 is manganese dioxide or manganese 4 oxide, and that acts as a catalyst. This is black powder. You mix it up, you mix the white KClO3 with black MnO2, it looks black. And then you heat this up. And what happens is the KClO3 decomposes, generates oxygen. And then what you do is you capture the oxygen. This is a tube filled with water, inverted, and the oxygen just bubbles up here, and then we can capture it here. When you capture the oxygen, then we can measure the volume of oxygen generated, we can measure the temperature of the oxygen generated. And we can measure the pressure. Well, the pressure, what we do is we just equalize the pressures. So right now the pressures are different, you know, atmospheric pressure and the pressure of the oxygen. We can do that, but there's one problem. The one problem is when you bubble oxygen through water, it saturates the oxygen with water vapor. And so when you bubble this, the oxygen in here is at 100% relative humidity. It's very humid oxygen because it's been saturated with water vapor. And so what we do is we use Dalton's law. We can measure the pressure of this in here, the gas in here, but that pressure of the gas here is the pressure, total pressure of the mixture. And so we can do that. So in this example, oxygen is generated for laboratory experiment by bubbling the gas through water, as illustrated in figures 15.3 and 15.4. The total pressure of the oxygen saturated with water vapor is 755.4. The temperature of the gas mixture is 22 degrees C, and the water vapor pressure at that temperature is 19.84. What is the partial pressure of the oxygen? Now, 100% relative humidity just depends on the temperature. So 100% relative humidity is always the same. And so that humidity is often given in terms of water vapor pressure here. All right, so what you can do is try to visualize this gas mixture here in terms of Daltons and in terms of Avogadros. And then what we want to know is either how much oxygen is in this mixture, pure oxygen. That is either the volume of oxygen or the pressure of the oxygen. And so this is the situation we have here. The oxygen is being generated. Initially, what's inside this tube? Do we have water inside this tube? No. And initially, what's inside this tube is air. And over here, it goes air and then eventually goes to water. We'll have water up to this level. And so the first thing is the oxygen that's being generated is going to be an Avogadro's mixture. That is, we have a fixed volume of air. And so what we're going to do is we're going to heat this up and generate the oxygen. The oxygen is going to add to the volume. And so in Avogadro's law, the volumes are additive as long as the pressure and the temperature are the same. So what we're going to do is we're going to make sure we know what the pressure of the air is inside here, and we're going to make sure we know what the temperature is. And then as we generate the oxygen, we got to wait until the oxygen is also at the same temperature and pressure, and that way the volumes add up. So whatever oxygen we add to this will show up here. And so this will be the volume of the oxygen vapor that's being generated. But the problem with the oxygen vapor that's being generated, so this is where we use two things to visualize this. First, it has to displace the air, and that's Avogadro's. And so we know the volume of oxygen is going to be whatever is displaced. The second thing is we're bubbling it through water. If we bubble it through water, then water vapor is going to saturate the gas. So oxygen we usually use for adding. And so this is what we call wet oxygen. It's humid, it's got humidity. If we have wet oxygen, it's a mixture of O2 and H2O gas. There are two ways to visualize this. One way is we can visualize this using Avogadro's. If we use Avogadro's, then some of this volume is due to oxygen. Some of this volume is due to water vapor. And so if we separate that into part of this volume is from the oxygen, part of this volume is from the water vapor. And so let's say I had 100 milliliters of this. I'd want to know, out of that 100 milliliters, how many milliliters of oxygen and how many milliliters of water vapor or gaseous water do I have? The other way of visualizing this mixture is using Daltons. If I use Dalton, then the volume is the same. The volume of oxygen that I generated is the same as the volume of H2O I generated. And so they're going to occupy the same volume. So let's say I generated 100 milliliters. I generated 100 milliliters of O2, which is here. And I generated 100 milliliters of water vapor. The water vapor can travel anywhere it wants in this container. And so instead, what I'm going to have is, instead of the volume, so this would be the volume of the O2 and the volume of the H2O gas, I'm going to be dealing with the pressure. And so the pressure of the O2 is going to be less. I'm just looking at the O2, not the O2 and the water vapor. The pressure of the water vapor is going to be less. And so here the pressures are additive. And so in Avogadro, V total, V of the mixture, is equal to V total, is equal to the volume of the oxygen plus the volume of the water vapor. In terms of Dalton's, the pressure of the mixture is equal to P total, which is going to equal the pressure of the oxygen plus the pressure of the water vapor. The pressure of the water vapor is in a table in the book. We assume 100% relative humidity. And then it just depends on the temperature. And so we have the temperature and the vapor pressure of water. Yeah. And so for this, it's much easier to use Dalton's because we can find the water vapor pressure in a book. And the water vapor pressure just depends on temperature. So the water vapor pressure at that temperature is 19.84. And so the temperature, whatever this is, we look it up in the table, 19.8 torr at this specific temperature, and then we copy it. And so this is equal to the pressure of the wet O2. And so the pressure of the dry O2 is equal to the pressure of the wet O2 minus the pressure of the water vapor. Basically, we want to figure out how many moles of O2 gas we have. So here, this is equal to the volume of wet O2. So if we use Avogadro's, what would we need to find the moles? The moles of dry O2 is equal to the pressure of dry O2 times the volume of dry O2 divided by RT, the temperature of the dry O2. The problem is finding the volume of the dry O2 because how much of that volume is due to the water vapor pressure? Well, we can actually calculate that too, which we'll do. Whereas over here, the moles of O2 that we generated will equal the volume of dry O2 times the pressure of the dry O2 divided by RT of dry O2. And so we use different volumes here and different pressures. Here, the volume of dry O2 is the same as the volume of wet O2. And the pressure of the dry O2 is just this. This is the pressure of the dry O2. And so we know the pressure of the wet O2, and we can just subtract the pressure of the water vapor from this. The actual homework problems are going to be a lot easier than what I'm going through here. And so let's look at actual problem here. Calculate the partial pressure of oxygen in atmospheres in the sample collected over water, given that the total pressure of the mixture is 0.98 atmospheres and the total pressure of the water vapor is 16.5 millimeters of mercury. So this is a typical problem here. We have a mixture of oxygen, gas, and H2O gas. P total is 0.98 atmosphere, and the pressure of the water vapor from the table is equal to 16.5 millimeters of mercury. And so what we want is the pressure of the oxygen, dry oxygen. Pressure of the dry oxygen is plus the pressure of the water vapor is equal to the total pressure. And so the pressure of the dry oxygen is just equal to the total pressure, 0.98 atmospheres, minus the pressure of the water vapor, 16.5 millimeters of mercury. Well, millimeters of mercury won't work here, so we have to convert that to atmospheres. So 1 atmosphere is 760 millimeters of mercury. And then we can get this in atmosphere. So conceptually, this is difficult, but calculation-wise, this is the type of calculation that you have. So calculations are not hard. I'll stop here. Were there any questions? This is collecting gases over water. So whenever you collect gases over water, we just use Dalton's. Figure it out. Right, we'll have the quiz at the end of lab tomorrow.